generate parentheses. So to solve this problem, we need to know dynamic programming. And the concept of dynamic programming is simply building solutions on top of each other. And this is best illustrated with an example. So we're given this example here where n is 3, and we're trying to generate all of these valid parentheses. And to understand what makes a valid parentheses, let's first understand that very problem. What is a valid parentheses? Well, it's simply this, right? For every opening bracket, it's paired with a closing bracket. So what this allows us to do is we can have nested brackets or side-by-side brackets like so. The only thing that we need to watch out for is that the number of opening brackets is equal to the number of closing brackets. So dynamic programming, we need to build on top of solutions. What do you notice about all these valid parentheses? Well, they always start with a open parentheses like so. So let's begin with the base case, which is a string of length 1 with just the open parentheses. When we have this, we can do one of two things. We can add one more open parentheses, or we can close it off. But how many open parentheses can we afford to add? The number of open parentheses we can afford to add has to be at most n is equal to 3. When the number of open brackets equal to 3, we cannot add any more. Therefore, one criteria we can establish is that the number of open brackets has to be less than n for us to add a open bracket. And what else can we establish? Well, let's continue building the tree. From the right-hand side, we can either add an open bracket or add a closing bracket. But this is not valid because the number of closing brackets is greater than the number of opening brackets. Therefore, another criteria we can say is that if the number of closing brackets, and we'll denote that with close, if the number of closing brackets is greater than the number of open brackets, then it's not valid, and we can just return. There's no valid solutions here. But when open is less than the number of less than n, we can add one. But when do we stop? When do we only add closing brackets? Well, let's keep building the tree. This, we can add one more. This, we can close it off. And this is still valid. So we could actually say that when open is less than n, we can add one, and we can add a closing bracket like so. And we simply stop when the number of open brackets is equal to n. Then we can only start adding closing brackets. So with this logic, let's implement this in Python. So the resulting output has to be an array. So let's call the resulting output res, and that will be an array. And this is a recursive solution. So let's build a recursive method within the method. So the method of solution will take in the number of open brackets, the number of closing brackets, and the current string. And when do we know to return the solution? Well, the solution is achieved when the length of the string is equal to twice the value of n, because you can only have at most n open brackets. Therefore, you must have a corresponding n closing brackets. So n plus n is 2n, and if this is achieved, then we must append the solution to the res, and we return like so. But how else do we check? Well, if the number of open brackets is greater than or equal to the number of closing brackets, what do? We must check if the open brackets is less than n. If it is, we can add more open brackets. So we do solution open plus 1 close s plus open bracket. And we can always do solution open close plus 1 s plus closing bracket, because if the number of closing brackets is greater than the number of open brackets, then we simply return, because there's no valid solutions there. So we always do this because we're going to catch all invalid solutions right here. Therefore, what do we do next? Well, we're done. We simply call the solution with 1, 0, open bracket as our base case and return res. So let's run it. And it's accepted, so let's submit. And that's the solution.